differentiating inverse trig. That's the one function or set of functions we haven't looked at yet. So inverse sine, how on earth are we going to do it? Well, fortunately, we now know how to differentiate sine. So how about I just rearrange this and make it x equals sine y. And instead of finding dy dx, I'll find dx dy. Because we know sine goes to cosine. So dx dy is cosine y. But we don't want dx dy, we want dy dx. So I'll turn both sides upside down. We get that dy dx is 1 on cosine y. Okay, well that's the derivative. It's in terms of y, but okay. Let's change it though so it's in terms of x. Cosine y I could rewrite as the square root of cosine squared. Cosine squared I can rewrite as 1 minus sine squared. And the second line there, we've got that x equals sine y. So I can now make it 1 over the square root of 1 minus x squared. So I have the derivative in terms of x. Let's do the same thing for cosine. So we'll change this to x equals cos y. Cos goes to minus sine. So we're going to get a pretty similar answer. So y dx is minus 1 on sine y. But we'll change the sine y, square root of sine squared, square root of 1 minus cos squared, 1 minus x squared. So the negative of 1 on the square root of 1 minus x squared. All right, let's do tan. Make x equals tan y. So dx to y is sec squared. 1 on sec squared, but sec squared I can rewrite as 1 plus tan squared, and we get 1 plus x squared. So notice no square root on that one. Okay. So to summarise that and to generalise it at the same time, if it is a linear function, think of it as x on a. And if it's x on a, we'll get 1 over the square root of a squared minus x squared for inverse sine. For inverse cos, we'll get negative 1 on the square root of a squared minus x squared. And for inverse tan, we'll get a on a squared plus x squared. Now be careful, because notice these first two both have 1 on the top. The tan has a on the top. That's why personally I prefer to generalise it and go inverse sine of function x, because then all three are very similar. I can say that the inverse sine will be the derivative on the square root of 1 minus the function squared. Inverse cos will be minus the derivative on the square root of 1 minus the function squared. And inverse tan will become the derivative on 1 plus the function squared. So they all have the derivative on top. Let's do some examples. So inverse sine of 5x. If I use the second one, the derivative is 5 on the square root of 1 minus the function squared, the square root of 1 minus 25 x squared. Inverse cos ex, minus the derivative, minus e to the x, over the square root of 1 minus the function squared, so it'll be e to the 2x. Inverse sine of x on 3. Well, that is where the first one would be useful. Because if it's x on a, I can write 1 on the square root of a squared minus x squared, and I've got it straight away. If I still use the other way, it'll work, of course. Derivative on the square root of 1 minus the function squared, but we've got fractions on fractions, so I need to multiply top and bottom by 3. Yes, it looks like the denominator on the bottom is 9, but it's not, because remember that's the square root of 9. So multiply top and bottom by 3, and we'll eventually get 1 on the square root of 9 minus x squared. Same answer, of course. E to the power of the inverse cos of x. So it's an exponential function. So how do we differentiate exponentials? We differentiate the power, that goes to the front, and then it's e and the power doesn't change. So I look at the power and it's the inverse cos of x. So I'll get minus 1 over the square root of 1 minus x squared. That's the derivative of inverse cos x, but that'll be times e to the inverse cos x. And I'll just make that look a bit neater by putting that exponential to the top. The inverse tan of x cubed. Okay. Bring down the power, 3. Lower the power, 2. Diff the inside. Well, inside is inverse tan x. Differentiate inverse tan x, we get 1 on 1 plus x squared. Tidying all that, 3 times inverse tan x squared over 1 plus x squared. Product rule. Write down the first, x squared. Diff the second. Well, the second is inverse tan. So differentiate inverse tan, the derivative, 3x squared, over 1 plus the function squared, well, x cubed squared is x to the 6, plus, write down the second, inverse tan of x cubed. Diff the first, we get 2x. I'll tidy it up. I'm not going to bother factorising that. I don't think it makes it much neater. So 3x to the 4 on 1 plus x to the 6 plus 2x inverse tan x cubed. HSC question from just a couple of years ago. So we have this function, the inverse sine of x plus the inverse cos of x. There's the function. Show that the derivative is equal to 0 was the first part of the question. Well, if I differentiate inverse sine, I'll get 1 on the square root of 1 minus x squared. If I differentiate inverse cos, I get negative 1 on the square root of 1 minus x squared. Add them together, you get 0. Hence or otherwise, prove this relationship. Remember, it's our identity with inverse trig, you may recall. Inverse sine of x plus inverse cos of x is pi on 2. So what they're getting at there is, hang on, I've differentiated something and the answer was 0. Therefore, I must have differentiated a constant, because only constants go to 0 when you differentiate them. They're asking us to show or prove that that constant is pi on 2. The derivative is 0. They're both continuous functions over their domain. We know that. And function x is constant. All I've got to do is substitute in a value to find out what that constant value is. I'll substitute in 0, and we get inverse sine of 0 plus inverse cos of 0, which is 0 plus pi on 2, pi on 2. So we have our result. Hence, sketch the curve. And this is where the problem happened. There's my axis. Okay, pi on 2, there's the graph. It is not the complete line pi on 2, because the domain of the function, go back to what the original function is inverse sine x plus inverse cos x. Its domain is in between minus 1 and 1. That was the big mistake a lot of people made. They drew the line y equals pi on 2 and didn't think about the domain of the original function. So that was 2 years ago in the HSC, they asked that particular one. But that brings me to a similar question. Suppose we'd ask this one. Function x is inverse tan of x plus inverse tan of 1 on x. Starts off the same way. Show that the derivative is equal to 0. All right, differentiate inverse tan x, I get 1 on 1 plus x squared. Plus, differentiate inverse tan of 1 on x. Derivative, minus 1 on x squared, on 1 plus the function squared. Tidy up that second one and we get minus 1 on x squared plus 1. They add together to give 0. So similar to that last question. Okay, sketch it. Problem is with this one, again, it's a domain issue, but it's discontinuous at x equals 0. So when you substitute in to find out what this constant value is, if I substitute in x equals 1, and again I get pi on 2, amazingly, same thing. Pi on 2, but if I sub in negative 1, I get minus pi on 2. So again, the mistake people would make with this one is go, oh look, I found out it's pi on 2, I'll just draw y equals pi on 2. Forgetting, let's draw it, there's pi on 2, forgetting that it's discontinuous at 0, and so that is actually the graph. So when it's positive, it's pi on 2, and when it's negative, minus pi on 2. So be careful. Make sure you take into consideration the domain of the actual function with that sort of question. And 12a, let's play.